All right, Dian, you can start when you're ready. Okay.
Okay. Hello, everyone. Today, I'm going to present a paper published in NIPS 2020. And the title is Storage Efficient and Dynamic Flexible Runtime Channel Pruning by Deep Reinforcement Learning. And here is the outline. Firstly, I'm going to give you the backgrounds and motivations. Next is their proposed deep reinforcement learning based pruning framework. In this part, I will introduce the system overview, some key components, and their deep reinforcement learning model. Finally, I will conclude this paper with the performance evaluation part. Next, let's look at the backgrounds and motivation. In recent years, convolutional neural networks have demonstrated a remarkable performance in various computer vision tasks. However, since most CNN models require expensive computation for the inference and a huge storage space to store large amount of parameters, therefore, the limitation of energy, computation, and storage on mobile or edge devices has become the major bottleneck on real-world deployments of CNN models. To solve this problem, there are some existing solutions, including the network quantization or network pruning. In this paper, we focus on one type of the network pruning methods, the channel pruning, where we can prune the channels to reduce the network parameters. Let's see the details of channel pruning. Firstly, we look at the differences between the channel pruning and the filter pruning. This is the framework of the CNN network. Firstly, for one input feature, we can use the filters to convolute it and get the output feature maps. So filter pruning means we remove the whole filter, thus resulting in remove the channels in output feature map. That's the filter pruning. And the channel pruning means we also want to remove the whole channels of the input feature map as shown in layer I+1. We prune the weights of all filters in the same location to achieve that goal. It should be noticed that these two methods are correlated. Pruning a filter in layer 1 is equivalent to pruning the corresponding channel in layer I+1, and they have a same effect on the weight parameter reduction. In this paper, they focus on prune the output channels, although they call their method a channel pruning. I think they still prune the filters, and actually it doesn't matter which method they use because both of them have the same effect. That's the differences between the channel pruning and the filter pruning. And most channel pruning approaches can be categorized into two types. One is.
I have a question here. So can go back to the previous slide here. So yes. For the filter pruning, they are trying to reduce the number of filters.
Yes.
So here, for example, in this figure, you have six filters. So they want to prune 2 filters.
Yes.
Then why don't they just design, 4 filters instead of 2 filters? So what's the pruning effect here? I mean,
actually, we have a pre-trained model and it contains 6 filters. And then we do the pruning part. We can prune some filters. We can prune some useless filters.
Okay, so the network has already been well trained using these 6 filters.
Yes. Yes.
Oh, okay. So you just trying to
reduce the parameter. Yes.
Okay, got it. Thank you.
Okay. And most channel pruning approaches can be categorized into 2 types. One is a static channel pruning, and the other one is a runtime channel pruning. A static channel pruning aims to evaluate the performance of each channel over the whole training dataset and remove the latest important channels to minimize the loss of performance after the pruning. So although we in this channel static pruning approach, although we have different input features, but we have the same pruning structure. So it can permanently prune some features and dramatically reduce the computation and storage cost. And for the runtime channel pruning, it can achieve dynamic channel pruning on each individual instance. For different input instance, we prune different channels. So we call it runtime channel pruning or dynamic channel pruning. And this kind of approach is able to significantly improve the representation capability of a CNN network, and thus achieve better performance in terms of prediction accuracy compared with the static approaches. But for this runtime channel pruning, we need to store all parameters, so it will not save the storage space. And in this paper, they consider both the runtime channel pruning and the static channel pruning, and propose a deep reinforcement learning based pruning framework. And in their method, they can achieve the high dynamic flexibility, which means they have the higher accuracy. This is the advantage of the runtime channel pruning. And also they can save the storage cost, and they can reduce the storage cost. And it is the advantage of the static channel pruning scheme. And the channel pruning strategies can be automatically generated by the deep reinforcement learning agent. And their method will also satisfy the overall budget constraints and preserve the network's training accuracy. So that's the contribution of their paper. Next, let's see the details. Let's see their deep reinforcement learning based pruning framework.
Dian, I just have a lot of questions. So can you go back to the, you laid I think the runtime channel pruning, previous one, yeah. This
Yes.
one, the runtime channel pruning, you mean that you give, for example, you give a different test image. I'm going to give you a different pruned model.
Yes.
But what if that's the case? Are you going to do some extra operation in order to decide? Because for the static channel pruning, you have already you can determine which filters has been deleted or which channels has been pruned beforehand. So you don't need to do that during the inference time. But for but for the runtime channel pruning, looks like it will be slower, right?
Yes, I think for runtime pruning, the advantage is the better performance. We can preserve the accuracy.
Oh, so they can preserve accuracy, but they are
introduce more computation compared with the static channel pruning, but we can still save the time compared to the original model and improve the accuracy compared with the static channel pruning.
Oh, okay. So, but runtime channel pruning, the time, I mean, the delay should be higher than the static channel pruning, right? But it's
it depends on how many channels you prune. If you can prune more channels, I think the inference time can also be reduced.
Oh, okay. Oh, I see. Yeah,
Yes.
Okay, I see. Okay, thanks.
Okay. Now let's see their algorithm. Yes, and this is a system overview of their algorithm. For the input features, they learn two types of channel importance predictor. They have the runtime channel importance predictor and the static channel importance predictor, which can measure the importance of each channel. And also they have two deep reinforcement learning agents, the runtime agent and the static agent. They can produce the actions as the sparsity ratio or pruning ratios for each layer. Finally, by combining all these components, by combining all these four components, they can generate a trade-off pruner to balance the runtime pruning and the static pruning, where we can prune the output feature map and get the final results. So this is an overview of their pruning framework. framework. Next, let's see the details of each part. Firstly, we look at these two vectors, the runtime channel importance vector UR and the static channel importance vector US. UR and US are two vectors, and there are the number of C elements in each vector. C is the number of output channels or the number of output filters. So we can use these two vectors to measure the channel importance of the output feature map. Next is the sparsity ratio. We also have two types of sparsity ratios, the runtime sparsity ratio and the static sparsity ratio. And these two terms can be obtained by the deep reinforcement learning framework, and it will indicate that how many channels to be selected during the pruning. Finally, we will have our trade-off pruner. We will have two terms, the M term and the U term. M is a binary decision mask, where 1 means we need to prune that channel, and 0 means we need to preserve that channel. U is a unified channel importance vector, which will be related to the UR and US. Therefore, we will have our pruning results as shown in this equation. We use the output feature map F out times this decision mask M, and then times this importance vector U. And in this function, 1 is the matrix of the same size as M, with all the elements being 1. So some channels are selected to be pruned during this equation. That's some details of their system overview. Next, let's see how to obtain these 4 vectors, how to obtain this importance vector and this sparsity ratio. Firstly, let's look at how to obtain the runtime channel importance vector UR. The UR can be predicted by a runtime importance predictor F, whose values vary over different input instances. And in this paper, they use a neural network. They use a subnetwork to approximate this runtime importance predictor. So the input of this neural network is the input feature map, and the output of this neural network is the runtime channel importance vector of the output feature map. Although this paper, they didn't show the details of this predictor, they didn't show how to train this neural network, but I found the solutions in another paper called FBS method. As shown in this figure, this flow represents the original CNN operations, and the network in the pink rectangle is the proposed subnetwork. So the input of this subnetwork is the feature map, the input feature map, and we feed this input feature map to a neural network. This neural network is our runtime importance predictor approximator. And finally, we will get the results. The output is the channel importance vector, and we can use this channel importance vector to multiply the output feature maps and obtain the final results. And when we do the back propagation in the fine-tuning part, in the fine-tuning process, we can also update the parameters of the subnetwork. Then we can also the parameters of this runtime importance predictor. So that's the design and the training process of their proposed runtime importance predictor. If we have trained the model, we will predict the runtime channel importance for each layer. That is the runtime channel importance vector UR. Next, let's move to the.
So go
okay.
Here, how are you talking about the training here or just about the inference here? I mean, in this figure.
I think is a fine-tuning stage. After we have trained the model, next step is we want to learn this runtime importance predictor. So we fine-tune this model and get this predictor.
So you fine-tune it. So file tuning is still the training stage, right?
Yes, yes.
So you mean that when you so this is more like an actual training stage that you want to use to learn this importance predictor.
Yes, because for the general pruning framework, firstly we have a pre-trained model, and then we prune some channels or some filters, and we need to fine-tune this model to achieve a better performance. So for the pruning stage, we always have the fine-tuning part.
So before so for the pruning, even if you have a pre-trained model, you delete something, but you are still going to file tune it.
Yes.
Okay, I see. Okay, thanks. Yeah.
Okay.
So Dian, what's the metric for the runtime importance?
It should be a probability from 0 to 1.
No. What I mean is, say if you put a probability, say like 0.9.
Okay.
What does it mean physically?
If from this paper, it means for example, if the runtime importance is 0.9 or 0.8, which means that this channel is very important, and we will have the higher probability to preserve that channel. We don't need to prune that channel. If the importance is, for example, 0.1, which means maybe we need to prune that channel.
Yeah, but somehow you need to determine, for example, if you don't prune anything, right? So you're going to have a result, right? If you prune something, you have the other result, right? Do you do any kind of comparison to decide which channel is important?
I think it can be learned during the fine-tuning stage. For example, if we prune some channels and we have the worst result, maybe for this learning stage, we will set the parameters of the channel importance of this channel will be higher. For example, if we prune some channels, we can still preserve the performance. Maybe the importance ratio of this channel will be very low, and I think it can be automatically learned during the training, and we don't need to design these vectors by ourselves. We use the neural network to learn them.
But it needed so many inputs, right? So do we say classify the input into different category or something? So how can we say, this model is well trained or something, right? We fit in so many inputs in there. We do the offline training, something like that.
Yes, we need to do the offline training before the inference stage.
Okay, so this is learning model specific, or is so I want to prune a CNN model or RN model, right? So for each, yeah.
I think they mainly focus on CNN, since only in the CNN we have this channel or the filter.
Okay.
Yes.
Okay then. Okay.
Okay, so let's move to the next page. In this page, I will introduce how to measure the static channel importance. Similar to the runtime channel importance, it still can be predicted by a static importance predictor H function, which can capture the global information for pruning. And again, we still use a neural network, a subnetwork to approximate this predictor. And the input of this predictor is some key features of the filter. And the output of this predictor is the channel importance vector US of the output feature. And here we define the K as the convolutional filters in this convolutional layer. So we have the number of C out convolutional filters in each layer. Here, they propose 3 key features to represent the filter. The first feature is a norm, and the second feature is a filter distance. We want to calculate the distance between each filter and the average filter. And the third term is the Hessian diagonal. Due to the computation complexity of the Hessian matrix, they approximate the Hessian diagonal using square root of the first order Taylor expansion. And the result is shown in this equation. And after we having these 3 key features of the filter, we will establish our predictor. For our predictor, we have 4 input components. The first 3 are the features generated by the pre-trained backbone CNN. So, if we already have the model, if we already have the convolutional filter, we can calculate these 3 features for each layer. And the fourth component V is a vector. It is a vector. It is randomly initialized and can be learned through the back propagation stage. And this V vector is a layer-wise vector, which means it will be related to specific layer. And therefore, we will have our prediction model. H is a subnetwork. We can still use the methods mentioned in the previous page to train this neural network. And finally, we will have our static channel importance vector US. Next, I will based on the
So here, what is the difference between, for example, this predictor and the previous predictor? Looks like their input and output, the input looks like very different. So what's why?
Yes, because for the runtime channel importance, for different input, we may have the different channel importance. So we put the input feature as the input of the layer. And for this static channel importance, for different input, we have the same static channel importance. So here we treat the filters, we treat the features of the filter as the input. It will not be dependent on the input data.
But even for that, even enough for the runtime importance predictor, it should also depend on the filters, right? But now it looks like you only depends on the input feature. I mean, the input should be include both input feature map and also the filters, right? The filter features.
Yes, for example, if we focus on the layer, for example, if we focus on the layer I+1, the input feature of layer I+1 will depend on the output feature of the layer I. It equals to the output feature of the layer I, and it will depend on both the input feature and the filter of the layer I. So I think even though we only consider the input features, maybe we still consider the filters feature.
Okay. But how about so are you going to learn this predictor layer by layer?
Yes, it will be learned layer by layer.
So
for each layer, we have a subnetwork.
So for each layer, you have a subnetwork. Are you going to, for example, are you going to learn those networks on different layers sequentially or in per layer?
I think it's sequentially.
Yeah, looks like according to your explanation before, it's more like a sequential. At first, I need to learn the first layer, the importance predictor for the first layer. Then I use the from the first layer as the input to the second layer.
I think this process can be integrated into the general training process. For example, if we update the parameters of this convolutional layer, we can also update the parameters of this subnetwork. It can be integrated into the training process, into the original training process.
Yeah, maybe. Yeah, looks like they should. I think they should steal the same back propagation step.
Yes.
To update a different set of parameters.
Yes.
Yeah. Okay. Thanks.
Okay. So, based on the obtained channel importance, they will design a trade-off pruner to generate a unified channel pruning decision. It contains two stages. The first stage is they prune some channels that are decided to be pruned by both of the runtime and static pruning scheme. And the second stage is they will also prune a portion of the rest channels by weighted votes of those two components. Next, let's see the details of these two stages. Firstly, for the first stage, assume we already have this sparsity ratio, and it can be obtained by the deep reinforcement learning agent. I will introduce how to obtain this parameter later. So we have the sparsity ratio, and we also have the runtime channel importance. Then we can generate a runtime decision mask. We will prune some channels with the smallest importance values according to this ratio and according to that vector. Similarly, for the static sparsity, for the static pruning, assume we already have the sparsity ratio AS, and we have the static channel importance vector US, and then we can generate a static decision mask. And some features can be included in some channels can be included in MR, and some other channels can be included in MS. And finally, we will generate a unified pruning result. Here we take the logic AND operator between MR and MS. So we have our pruning results M0, which means the channels are selected by both the runtime pruning and the static pruning. So this is the first stage. And for the second stage, firstly, we generate two new masks, MR bar and MS bar. MR bar means the channels are only selected by the runtime pruning, and MS bar means the channels are only selected by the static pruning. And the second step is that we define a hyperparameter RR. It indicates how much we choose the runtime pruning. So we will generate a new decision mask, MR height. It can select the first CR prime smallest important channels in the runtime pruning channel set. For example, if RR equals to 0.3, and there are 100 channels in this MR bar set. So therefore, the CR prime should be equals to 30, which means there are 30 channels in this MR height set. So that's the physical meaning of this MR height. And also for this static channel pruning scheme, we can generate a new mask, MS height, which is related to the static channel pruning. And here we choose the parameter 1 minus RR in this set. And finally, we will have our pruning results. It will be related to M and U. M is our final trade-off pruning mask. It will contain the M0, MR height, and MS height. And U is the final unified channel importance vector. It equals to UR multiplied the US. And based on this M and U, and we can have our final pruned results F alt height. So this is their designed trade-off pruner. Next, let's see how to get these two sparsity ratios by the deep reinforcement learning agent. Firstly, let's look at the runtime deep reinforcement learning agent. For the state space, we have this input feature map fin, and then we feed this fin to a global pooling layer to reduce its dimension to RC in. And next, we will feed this RC in to a layer dependent encoder, and we will get a fixed length vector STR. It is a representation of the original input feature map. We can use this term as the state. And for the action can be defined as the sparsity ratio for each layer. And here we limited the minimum value of this sparsity ratio. So this is the action space of the reinforcement learning. Next, let's see the reward function. It will include two parts. The first one is accuracy, and the second one is the computation consumption. For the accuracy, we define the accuracy reward as the minus of the loss. Since this loss may vary in scale among different training stage, for example, large at the beginning of the training and small near the convergence. So therefore, they normalize this loss by a moving average factor beta B, makes the training stage more stable. And for this computation consumption, they have a computation budget. So if the computation consumption is larger than this budget, we will add a penalty term to the reward function. Otherwise, this penalty will be 0. So the final reward can be defined as the accuracy reward plus the computation reward. It should be noticed that if the last layer is if it's the last layer of the neural network, which means the small t equals to the capital T, the reward is calculated with this function. Otherwise, we set it as 0. And for this deep reinforcement learning model, since both the state space and action space are continuous, so they use the proximal policy optimization method to solve it. It is an actor and a critic framework. And this is their deep reinforcement runtime deep reinforcement learning agent.
So so here, what is the T? T is the layer. What do you mean by time step here?
T is the layer.
But T is also the time step, right?
Yes. For example, for the first time step, we are in the first layer, and for the second time step, we are in the second layer. And for the capital T time step, we are in the last layer.
So it's still, I think it's still related to my question before. It's basically like they are specify or prove the network layer by layer. They first prove the first one, then the second one, third one, until the last one. Then they get the final performance results.
Yes. So for each layer, we have one pruning ratio. We have one sparsity ratio.
Okay, but only the last time step you get a reward.
Yes. Yeah. Yes.
Okay. Is this normal? I mean, usually I saw that for the deep reinforcement learning, in order to get a good performance, you should have some reward singular in each time step, right? Not just not necessarily the. I mean, for this reward function, well, only the last time step you have the reward, the other time step you only have 0. Is this normal? Is this common?
Yes, I think it's a common setting. For some scenarios, only when we arrive the destination, we will have a reward. Otherwise, we set the reward equals to 1 or -1. It's a common design of the reinforcement learning.
Okay. But how about the accuracy here? How do they So the looks like you only care about this one when t equal to capital T, right? But you also have the so-called B here, the moving average, the B here. So what's the difference between B and T?
For this B, I think B should be equals to T. For example, we have initialized the B and we update this B in each layer.
Yeah, but I think according to here, right? According to this one, looks like they only care about this value when T equal to capital T, right? But how in this case, why you have a beta here? This weighted average, because before the value is 0. Why?
I think the motivation is, for example, during the initial stage of the training, this loss should be very large, and in the later stage or near the convergence stage of the training, this loss will be very small. So they want to normalize the loss during the training.
Oh, so then the B is more like the B should be, so B
should be a scaling vector, I think. For example, in the item or momentum-based optimization method, we always have this factor to normalize the gradients we used.
But I think that then in this case, the B should be mini batch. I mean, for the first batch.
Yes, the mini batch index, I think is.
Yeah.
Yes.
Okay.
Yes.
Okay. Makes sense now. Yeah. Okay. Thanks.
Okay. So let's move to the static deep reinforcement learning agent. And for the static deep reinforcement learning agent, we need to determine the sparsity ratio. We need to determine the static sparsity ratio for each layer. And for this static deep reinforcement learning model, we directly use the output feature map as the state, and we use the static sparsity ratio as the action. So the reason although they didn't mention the reason they choose the output feature map, but I think the reason is that for the runtime stage, for the runtime scheme, we need to focus more on the input feature map, since the pruning strategy is highly related to the input. And for the static pruning, we need to focus more on the output feature, which is more directly. And for the reward function, they also includes two parts. One is accuracy, and the other one is the storage space. It is related to the number of parameters. So we have a storage budget. If the number of parameters is larger than this budget, we will add a penalty here. Otherwise, we will set this penalty equals to 0. And also the reward function can be defined as the sum of the accuracy reward and the budget and the storage reward. So that's the static deep reinforcement learning agent. And next, let's move to their training stage. I will show you how to train their network. So the input of their method is a pre-trained backbone CNN, and the computation and the storage budget. And the output of their method is, and what we want to get of their method is we want to get a fine-tuned CNN, and also we want to get the runtime importance predictor and the static importance factor, and also we need to get two deep reinforcement learning agents to determine the sparsity ratio. And the third step is we set the static importance vector equals to 1, and we set this two sparsity ratio equals to 1, 2. Then we will execute our training process. And for the step 5, we fix this static importance vector and update the runtime channel importance predictor in step 5. And in step 8, we update both the static and runtime channel importance vector. Therefore, for the step 4 to 9, we will get the channel importance predictor, or we will get the channel importance vector. Next, we will move to the deep reinforcement learning part. We want to use the deep reinforcement learning agent to make the decisions of the sparsity ratio. So for the step 13 and 14, we will update our deep reinforcement learning models to update the sparsity ratio. And here we fix the channel importance predictor and we fix the channel importance vector. After several epochs, we fix these deep reinforcement learning agents and try to update the static and runtime channel importance predictor again. And we repeat these processes until it converges. And finally, we will have our sparsity ratio. Therefore, according to this training process, we will get the channel importance predictor or the channel importance vector. We can also get the sparsity ratio for the runtime scheme and the static scheme. And that is the training process of their method. Next, let's move to the inference stage. We know that the static pruning strategy does not depend on the individual input data sets. So the static sparsity ratio AS and the static importance vector US are fixed. Therefore, we can prune some channels with H smallest static importance values. We can prune these channels permanently before the inference stage. Next, let's see how to calculate this H. How to calculate the H? What's a specific value of this H? According to our trade-off pruner, the channels selected by both the runtime pruner and the static pruner should be pruned firstly, which means we should prune the channels M0 firstly. And then with the probability 1 minus RR, the channels only selected by the static pruner are also need to be pruned. And the number of channels in this blue circle, MS hat, is H. So that's why, so the channels can be determined by the static channel should be M0 plus MS hat. And at least we need to prune MS hat channels recommended by the static scheme. So it will be save the storage space if we prune these H channels preeminently before the inference. And after taking this static pruning, we will move to our dynamic pruning part. We will prune other channels by following the pruning framework dynamically. And finally, we will have our pruning results during their design. Next, let's move to the performance evaluation part. They take their experiments on CFAR10 dataset, and they have two comparison baselines. They are both the runtime pruning methods. One is the FBS, and I have already introduced this method in the previous. In this method, we have the runtime channel importance predictor, and we use this predictor to determine which channel we need to prune. And the other one is RNP, is still a reinforcement learning based pruning method, where they group the feature during the training and prune them directly. And for fair comparison, they set the sparsity ratio as 0.5 for all methods. But for their proposed method, since we cannot set the sparsity ratio, so the computation and storage budget constraints in their method is calculated according to the sparsity ratio of other methods. And here they show the simulation results. From the simulation results, we R1 means that we solely consider the runtime channel pruning, and RR equals to 0.5 means we consider both the runtime pruning and the static pruning. And from this table, we can find that their performance, their methods outperform the other methods in terms of the final accuracy, the number of parameters, and also the time consumption. And the speed up here, speed up is calculated on max multiply accumulate operation. It's a specific type of the operation, and it is related to the computer architecture and hardware design field. And from this figure, we can find that the speed up, their performance is very similar or comparable to FBS methods. And for all the other metrics, their methods perform better. So that's the simulation results they provide. And they also take the experiments on other data set with other model, and they have the similar results. Their accuracy will be the highest one. And also they have some observations. This figure 2 shows the performance of various sparsity ratios in their method, and demonstrate that their method holds the accuracy when the sparsity is larger than 0.5. And the figure 3 shows the trade-off between the runtime pruner and the static pruner by adjusting this RR term. RR determines how much we trust about the runtime pruning. So according to this figure, with RR equals to 1, the accuracy becomes higher due to the more dynamic network flexibility, but the space of the parameter storage also increases. So this RR term can trade off the accuracy and storage. It can trade off the runtime pruning and the static pruning. Finally, let me conclude this paper. This paper, they present a deep reinforcement learning based framework for deep neural network pruning in both the runtime and static scale. They provide a trade-off pruner to balance the storage and the dynamic flexibility. And their proposed method outperforms the existing approaches in terms of the final accuracy and the computation overhead. And that's all for my presentation. Thank you for your listening.
Any questions? Dian, I have a quick question. Could you go to the constraint of runtime pruning and static pruning? I wonder why the static pruning, they consider the trade-off between accuracy and computing capability, but for the runtime, they consider the accuracy and the storage.
Okay, so since for the static pruning, we can save the storage because some channels can be permanently pruned according to this static pruning. So we focus on storage space on this static pruning part. And for the runtime pruning, because they cannot save the storage, so we mainly focus on the time consumption. So that's why we have different budgets, we have different constraints for the reward function.
So for runtime pruning, it's like
we need to store all parameters and prune the channels dynamically. So it will not save the storage space. It can only speed up the inference.
Okay.
Yes, but for the static pruning, and we can save we don't need to store all the parameters. So we can save the storage.
Hmm. So another question is, for the sparsity ratio, right? So is that going to be related to, is that going to be related to the arms? So how many channels you prune or something? How many filters you prune? Could you show me the figure?
Yeah. I think it's for the sparsity ratio is a probability. It will times the total number of channels in each layer. Here, the sparsity is a probability. For example, if equals to 0.2, we have 100 channels, which means we preserve 20 channels and we prune 80 channels, the number of 80 channels.
Yeah, but still, if you show that you have static pruning, running pruning, there's a two map, they have some overlaps, right? So,
yes, here.
Yeah. The thing is, for example, for the runtime pruning, you need to satisfy its sparsity target, right? For the static pruning, you also need to satisfy its sparsity target, right?
Yes. For example, for the whole model, we have a large rectangle, and then according to the sparsity ratio, we will determine some channels to be pruned by the runtime pruning. We will determine some channels to be pruned by the static pruning. It will be related to the whole channels in each layer and also the sparsity ratio we determine.
But the thing is, their algorithm, you do that. Do you do that iteratively, or you do that in a single round? So, because the sparsity ratio is kind of dynamic, yeah.
Yes, I think for this static sparsity ratio, we do it one time. Since after we decided it, we will fix it. But for the runtime sparsity ratio, I think we make the decisions dynamically, which means these channels will be fixed, but these channels will be dynamically changed.
Depends on different input, right?
Yes.
But in your inference stage, you still need to do the deep reinforcement learning, or you pre-train that.
We pre-train that. We just use it.
Okay, so for any kind of inference input, you already know which channel you need to prune for static one, also for the runtime one, right?
Yes, yes.
Okay.
So there are so there's a lot of pruning or pruning work there. So what's the new thing here? I mean, compared to the state of the art.
Okay, so I think there already have some papers use the deep reinforcement learning agents to make the decisions, but most of them, they only consider the runtime pruning or the static pruning. And for this paper, I think this is the first one to combine these two parts and generate the decisions automatically, generate the layer-wise decisions automatically.
But how about, but because you are using a deep reinforcement learning approach, well, the computation cost of the DRL is already very high. How do they, so you perhaps, you can get a better action or a better pruning strategy But you are using a very computation expensive operation or process.
Yes, but the computation overhead is happened during this training stage. For the inference, if we only use the deep reinforcement learning model to make the decisions, I think it will not consume too much time.
But that's a good point. So, but how about the runtime pruning? I think that's the inference stage, right? Because at that time, you will be able to load the testing image, right?
Yes, but still, again, for the runtime pruning, we only need to use this deep reinforcement learning agent. We only need to use this pre-trained deep reinforcement learning agents. We don't need to train this agent during the inference stage. So it will not introduce too much overhead.
Oh, so this DRL agent is still are still trained based on your training data.
Yes.
Oh, okay, I see. Yeah, but yeah, I still, I kind of get your point. Yeah, it's kind of like a hybrid version of those two approaches. But I still don't know how do they, so they in their performance evaluation, because there are so many different methods, right? So are they, how do they give a comprehensive comparison in that case?
Yes, and I think they also show their simulation results with other methods, but I think they mainly focus on this top one accuracy, because for the other metrics, maybe they will not outperform other methods, but for this top one accuracy, they always have the best results.
Why? So here, I saw that I saw their method is more like it's a better trade-off between this accuracy and the speed, right? So
yes.
I saw if that's the case, you are going to, let's say, we first fix the, for example, fix the time, fix the speed up time, and then we just compare the accuracy, or we just fix the accuracy, we compare their speed up time, right? I saw that you have to fix one axis in order to compare the other.
But I think it's difficult to fix the accuracy or to fix the speed up in yes, for example, how can we fix the accuracy? We don't know how to fix it. We only, what we can do is we can train the model until converge and to see the speed up and the accuracy.
So today, for example, I saw that before you mentioned there are some budgets, right? The storage and the computation budget, things like that. So do they fix the budgets for example, if that's the
yes. As I mentioned, they fix the sparsity ratio. Say, for example, for the sparsity ratio, they set the sparsity ratio for all other methods. They use the same sparsity ratio, but for this method, they cannot set the sparsity ratio because this one will be generated according to the deep reinforcement learning agent. So we cannot fix it. So we use the constraint, which is related to this sparsity ratio.
Yeah. Even for that, I think what Dr. Guo's meaning is you can still do the trade-off, right? Because in this paper, they mentioned the trade-off between the accuracy and computing the storage budget, right? They mentioned something like that. But I believe, I guess, okay, in their evaluation, they already fine-tune the stuff and pick up the best performance and do the comparison with the other guys. Say, okay, if I do this, I sacrifice this computation storage budget, that's the best things I can achieve.
Okay.
Even I sacrifice more, yeah.
Maybe, yes. For example, if we choose another sparsity ratio budget, maybe we have different results. Yes, maybe.
Yeah, maybe for a given one thing, right? So I already optimize the cost of the other and present the best performance there and compare with other guys, you know, so.
Yes.
Yeah, I still think that, you know, the comparison here, you know, if we can fix the one thing, I assume that for any pruning, right, it's more like a trade-off between accuracy and runtime, let's say, right? And then if you really want to compare them, perhaps you can fix one, or if you can beat others, you know, outperform others in both aspects, then that would say that your performance is better. But otherwise, you know, for example, your accuracy is higher than others, but your speed is slower than others. So how can you say your method is better than others?
Yes, they assume that the speed up is similar.
Yeah, this one makes sense, but,
yeah, but
for the other table, probably,
You see the other table, I think, yeah, if you go to the, as you go to the end, I think the other table needs the more.
Yes.
Here, right? You say you need the more method, and then you find that their method, the accuracy is higher, but the speed up is not the best, right? It's not the best. You have other method, for example, the FBS looks like it's.
Yes.
So thinking, well, is there a great method or a great evaluation framework to compare different methods in this literature?
I'm not familiar with the pruning part. I'm not sure they have a common metric for the fair comparison.
But I think they should have some kind of they should have some kind of metrics or framework that we perhaps we don't quite understand. But because from my perspective, you know, it's fine. Okay, you propose one, you get this table. Looks like most of the time you are better. But it's still not that convincing, you know. So rigorously, I think it's still not very convincing, considering that actually there's a lot of tuning part here, right? If you have a lot of tuning here, well, I don't know. Yeah, maybe they have their own language.
Yes, since they only provide the table and they didn't give any explanations on that table, so I actually I don't know. Yes, I don't know.
I think they must be have. Maybe we need to ask some experts about those kind of domain expert about how do they compare this kind of fairly, or, you know, it's a fair comparison. But that's fine. The table here.
Yes, for most of the pruning paper, they because they are not actually implement on the hardware, so usually they compare with how many parameters they are prune, or how many float point are you going to calculate, or here as the MAC. They usually compare with these two metrics to show the effectiveness of the pruning.
So it's still the one metric is the accuracy, another one is the operation number. I mean the number of operations.
Yes, the how many floating points are going to operate, like here the MAC, or how many parameters to show
speed up.
Yes. The paper they do this.
But they can run on the server, right? The server cannot show the advantage of the new proposed pruning algorithm. That's what you mean, right?
You mean the time?
Yeah, I mean the speed up, right?
You can report the MAC. Yes, they just show this MAC because you can calculate this one.
That's true. That's true. But what I'm saying is, even for the server, they cannot show the advantage of the new pruning algorithm.
I think they
For mobile device, probably yes. We cannot show the advantage because it depends on the computer architecture, right? But how about the server?
I think it's because like for different GPUs, you're going to have different times. So it's because of their hardware design or something. So maybe a number of MAC is more fair. Yes, because each device you would even for the same architecture, you will have different times because of their design or something. So I think many of these papers, they just show the number of MAC or the floating point operations.
Okay.
Almost
the caption they show here, the speed up is more like calculated based on MAC, right?
Yes.
It's not like real world. Okay.
Yeah, you can calculate this one by your model actually.
But I think for Dr. Guo's question, I think is that depends on different CNN model. Like this table 5 is for ResNet 18, and table 6 is MobileNet. For that, the first table is another.
CFR 10 data set.
CFR 10, right? Yeah.
I get the point. Yeah, just don't.
Yeah, depends on the structure of those things and data set, I believe.
Yeah. Maybe they want to show. Maybe they want to show that depending on the network structure and the data set, on some data set they are the best because they can outperform both. They are the best in both the accuracy and the speed up. But in some data set, they may be best in accuracy, but they are not the best in speed up or things like that. Maybe they have some explanation there.
Conceptually, they should be the best, right? They combine the two things. I mean, for the other scheme, probably they only consider one side. So, but I don't know.
Yeah, but sometimes, I mean, you know, it's you can say that you combine the two aspects, both the runtime and static. But usually when you combine them, you just use very specialized, for example, static analysis. Another one is the very specific dynamic or the runtime things. So you combine those two, that's fine. But how about you have how do I know that you have to use the optimized static method and the optimized dynamic method, right? Even if each of them they are optimal in their own just individually, but when you combine them, they are not always the best, right? So I think
got your point. Yeah.
Yes.
Yeah, but anyway, do they have any kind of theoretical results?
No. That's all for the paper.
I mean, for example, some theorem, some proof that well, this one will work because of some kind of performance guarantees, things like that, or is just purely heuristic?
They don't have the theoretical parts, since I think because the reason is that for this importance predictor, we use the neural network. And for this pruning ratio, we also use the neural network. So it's difficult to derive yes.
It's hard to derive any kind of theoretical.
Yeah, maybe this is a system work. So this is their style. So this is normal. Yeah, I agree. Yeah.
It's not like a system. It's like learning and more like a simulation.
So you like the system, right? See the learning on the system, right? on hardware.
They do some experiment, but I don't think it's touch on the real system. It really depends on how can we define the system, right? So they still calculate the max things, It's not like you work on the server and show the advantage of algorithm. It's more like you know, the learning community experiments. You choose some model and data set, and you run it, and you call it experiments. It's not like our community experiments. Yeah.
Okay. I see.
Yeah, I think so. I think we are still recording, right?
Yeah. Okay. We can start recording. Yeah.